Hey everyone, I am Miss Hu, your physics teacher. In this video, we're going to be learning about analyzing graphs, where we will learn to state the relationship between two given variables, determine the gradient, determine the area under graph, interpolate data, and extrapolate data. So this is kind of an introductory concept in physics, and it's just learning about how to analyze graphs in more detail. So what I'll be covering in this video is a simple overview. Depending on what kind of graph you get in your questions, do learn how to answer the questions specific to that graph. But generally, we're going to go through the tools you're going to need to analyze graphs. So for this particular video, I'm going to be using a velocity time graph as an example. If you don't know what velocity is, please watch my video on velocity, which is in my scalar and vector video. And if you want to know more about how to analyze velocity time graphs, do watch the section on velocity time in my motion graphs video. So for now, I'm not going to explain this in more detail. We're just going to go into how to analyze this graph. So we're going to start off first by learning how to state the relationship. So when it comes to stating the relationship, it's about explaining the relationship between what's on the y-axis with what's on the x-axis. So when it comes to physics graphs, we don't say, the y variable and x variable. No, you have to specifically mention the variables on the y and x-axis. That means we're going to talk about the relationship between velocity and time. So in this particular graph, you can see that there are three sections. We have section A, section B, and section C. There is no single relationship over here because there are three parts of the graph. If you were asked for the relationship in your exam question, you have to read carefully and see which part are they referring to. So for the purposes of this video, I'm going to describe the relationship for all three parts of the graph. In terms of the description of the relationship, there are several ways to describe relationship. So you've got things like directly proportional, increasing linearly, inversely proportional, decreasing linearly. If you want to recall what all those different relationships are, please watch my video about the relationship between the y variable and x variable for various graphs. So for now, we're just going to dive into the answer for this particular graph. Let's take a look at A. As you can see, for section A, the graph is a linear line that starts from origin. So this shows us a directly proportional relationship. Remember that directly proportional is a straight line through the origin. Now, when you write the relationship, you cannot just write directly proportional. You have to state the variable of what's on the y-axis and on the x-axis. So how we write the answer for A is velocity is directly proportional to time. So that's the relationship in section A. For section B, you'll find that it is a straight line, but it is parallel to the time axis. So B is showing us constant velocity. There is no change in the velocity with regards to time. So I'm just going to write constant velocity. As for C, you'll find that the graph is a linear graph that is dropping down. Now, remember, this does not mean inversely proportional. Inversely proportional is when the graph is curved like this. So this is a straight line graph. It is a y equals mx plus c graph where m is a negative value. If you don't know what I mean, go recall your math or go watch my video. For now, let's look at how to describe this. This is a linear decrease. So velocity is decreasing. You can see the velocity is dropping, right? It's decreasing in what fashion? Linearly with time. That's how you can state the relationship for A, B, and C. Next, how do we determine the gradient? So again, there is no such thing as one gradient to represent the entire graph because there are three sections in this graph. So let's look at how to calculate gradient in general first. Now, depending on how your teacher teaches it, you might learn it with the formula as gradient is y2 minus y1 over x2 minus x1. Or you might learn it as change in y over change in x. Or you might learn it as rise over run. So whichever the formula you use, it's actually calculating the same thing. So because there are three sections in this graph, let's calculate the gradient for all three sections. So let's start with A. Now, every time you calculate the gradient of a graph, you must always show how you get the gradient from this graph. Now, make this a habit whether or not the question asks you to. Most of the time, you'll see that the question says, show clearly on the graph how you obtain the gradient. Even if the question doesn't ask, just make it a habit, because I've got a lot of students who forget to show this and they end up losing marks. How do we show this? Drawing the gradient triangle. How big should a triangle be? Now, every exam mark scheme does have a minimum size, but I wouldn't recommend you look for that minimum size. I find students, when they know, oh, there's a minimum size, somehow they always aim for that minimum size, but because they estimate it wrongly, it becomes smaller than the minimum size and they don't get the marks. To be on the safe side, always go big. Take the biggest triangle that you can get from that section. Can you start from 0, 0? Yes, you can. So for A, we're going to start from 0, 0, and we're going to take it right at the top over here. Show the gradient triangle, meaning you have to draw the triangle. Use dotted lines. Use a ruler, please. Draw the dotted line clearly, like so. And when you get the coordinates to calculate the gradient, especially if you're using the first formula, please don't just draw a random triangle and then you take two other random values in the middle. No! The gradient triangle you draw is based on the coordinates that you're going to put into your formula. So let's say we take the first formula in this case. So we've got the coordinates of 0, 0 and 4, 6. So the value here becomes 6 minus 0 for the top of the fraction. And for x, this is 4 and 0, so 4 minus 0. M in this case is referring to the value of the gradient. So you're going to get 6 divided by 4, which gives us 1.5. Do not leave your answer in fractions. Always write your answer out in decimal place. Before we move on, you got to check, does the gradient have a unit? So I've got a lot of students say, yo, gradient, no unit. No, just because you learn in maths there's no unit, that doesn't apply for physics. The reason why you've never learned a unit in maths is because you're only working with x and y. There are no units with x and y. You learn the gradient concept generally in math so that you take that general concept and apply in other subjects like physics. So now when it comes to physics, we're going to have to learn to be more specific. How do we get the gradient? Whatever unit on y-axis goes on top, and whatever unit in the x-axis goes at the bottom. So I'm just going to write here to point out to you. The unit on the y-axis, which is velocity, is meters per second. So I'm going to just write here meters per second. And the unit for the x-axis is seconds, which is for time. So meters per second divided by second. Meters per second divided by second, not times, yeah? Divided, you're going to get meters per second squared. So that's how we obtain the unit for the gradient. Now let's look at B. B is a flat horizontal line that's parallel to the x-axis. So if you know your math, obviously a flat line parallel to the x-axis is 0 gradient. So we're not going to calculate that because we already know it's 0, right? So I'm just going to write here 0. Now for C, this is our gradient triangle. So remember to always draw the triangle. We're going to take the two coordinates that are furthest away from each other to get the largest gradient triangle. I'm just going to add the triangle sign just to show you. That's the gradient triangle. So for C, the gradient is negative because it's going down. So if we use the formula correctly, of course, you're going to get a negative number. So for y2, we have 0 and y1 is 6. So I'm going to write 0 minus 6 for the top of the fraction. Whereas for the bottom of the fraction, we have 12 and 9. So that's 12 minus 9. So this gives us negative 6 over 3, giving us negative 2 meters per second squared. Same unit as A, obviously, because it's same set of quantities. So that's how you can calculate the gradient for the different sections of this graph. So by the way, in case you haven't spotted it, the gradient is actually showing us the acceleration. That's why it has the acceleration unit. Now, when drawing gradient triangles, just a reminder, always draw them with dotted lines and with ruler. Yes, I know my lines are not straight because I'm using my tablet. But make sure you draw the lines with dotted lines and not with solid lines. The difference is that solid lines are reserved for the actual graphs that are plotted based on the coordinates, whereas dotted lines are lines that we add on to help us interpret or analyze the graph. So gradient triangles are not part of the graph. They are lines drawn for us to help us analyze and calculate the gradient. That's why we draw dotted lines. Let's move on to how we determine the area under the graph. So depending on the question, sometimes the question could ask you to only count the area for one section. For example, calculate the area under B only. Or maybe they want the entire thing A and B and C. So depending on the question, you need to see where the start and where the end is and calculate the area for that particular section. So for the purposes of this video, we're going to calculate each three parts separately. Let's start off with part A. Now remember that when calculating the area under the graph, between the start and stop points, we need to have the vertical lines that go to the x-axis, and we calculate the area bordered by those two vertical lines, the line and the x-axis. So for A, our starting point is already at the x-axis, which is a time axis, so no need to draw any vertical line. This point, we're going to drop to the x-axis, and you can see here the area which I'm shading is a triangle. So when calculating the area under the graph, we don't count, 1, 2, 3, 4, 5, 6 squares. No, you look at the value on the axis. So it happens that, yeah, this is 6. But just to let you know, that you look at the value, because if let's say the numbers here were different, you need to take the number at this particular point of the coordinate. So triangle is what? Half base height. Let's put the numbers in straight away. The base is 4 seconds, so I'm going to write 4. And the height is 6. So half times 4 times 6. This gives us 12. Now, are there units for the area? Please don't say no. We've just learned that gradient has units. So that means area will also have units, right? Because physics, we have units. So how do we figure out the unit? Again, we're going to use the unit based on the axis. So half base height. The base here is 4 seconds, whereas the height is 6 meters per second. You can also cut when it comes to units. So just like with numbers, for units you can also cut because you can see seconds times meters per second. So this second you can cut with the second that's at the bottom of the fraction for meters per second. This gives you 12 meters as the final answer. Now look at B. So B, we have a rectangle. So I'm going to shade here. To calculate the area, we're going to get the length times width. So you can see here the length is between 4 and 9, giving us 5 seconds. So 5 seconds times the height, which is 6 meters per second. Again, we can cut the unit. Of course, you're going to get the same unit as with A, but just to further prove to you, all right? So we have 5 times 6, which gives us 30, and the unit is meters. And now for C, same thing. C is a triangle. So we have area, which is half base height. The base is between 9 and 12. 12 minus 9 is 3. So I'm going to write here 3. Unit is seconds. The height is 6 meters per second. So this would give us, again, you can cut the seconds. Half times 3 times 6 will give us 9 meters. So that's how we calculate the area under the graph for each of these sections. So if you needed to get the total area, then all we need to do is add them up together. So we have 12 meters plus 30 meters plus 9 meters. This will give us a total of 41 meters. So of course, if you wanted to calculate the total area, you could also use the formula for the trapezium. That's fine. Or you can use triangle, rectangle, triangle. You're going to get the same answer anyway. So by now you should have spotted that the area under a velocity time graph, as you can see, is equivalent to the displacement covered by this moving object. That's why we have the value of the area in meters. It's covered a displacement of 41 meters. Now let's talk about interpolating data. So interpolating data just means that we need to get the value in between the graph. Some of you may know how to solve this question without even realizing it's interpolation. It's just a fancy word here. As long as you know how to solve the question, that's fine. Let's just go into how to solve these questions. First question is, what is the velocity of the object at t equals 3 seconds? Now, one thing you must remember is that every time you get a value from the graph, you must show how you obtain that value. So that's why earlier when we had to calculate the gradient, you have to show the gradient triangle. For the area, you don't really need to shade it, but it helps. Now, for interpolation of data, to get the velocity at 3 seconds, you had to look up the graph, right? So make sure you show that you got the value from the graph. You're not just plucking the number from some random space in your head. So if the time is 3 seconds, that's over here, we draw a dotted line. And then from here, we look up the value on the y-axis. Okay, please use a ruler for this. I'm using my tablet, so obviously the line is not so straight. But use your ruler when you're looking this up. You get the value of 4.5 meters per second. Every time you draw a guideline like this, it has to be a dotted line. The difference between a dotted line and a solid line is that dotted lines are guidelines. It's something that we add on to help us interpret the data. A solid line like this is the actual graph line. So when we draw solid lines, this tells us this is the graph. Dotted line is a guideline. So by differentiating this very clearly, it helps anyone who's looking, especially the examiner, to be able to see, oh, okay, this is the actual graph in the question, and the student is drawing dotted lines as guidelines to be able to look up values. So even in the real world, outside of your exams, we take the same approach. So actual graph lines are always solid, so anyone who's looking at the graph knows, okay, these are the actual graph lines plotted based on data, but any data that we're looking up or any gradient calculation, this is shown clearly with the dotted lines. Now, moving on to the next question. What is the velocity of the object at t at 10 seconds? Same thing. You need to add the dotted lines to show this is where we're getting the number from. Please use a ruler and use a pencil to draw the dotted lines, and you get 4 meters per second. So to interpolate data means to find the additional value within the ranges of the graph. So inter. Now let's look at the concept of extrapolating data. So for this, we're going to be using a different graph because this graph is actually pretty complete. So extrapolation of data normally involves using graphs that are not quite complete. So for example, let me just move my face out of the way here. This graph is a hanging graph. A hanging graph here means that it's floating between the x and y axis. And just a reminder, especially for those of you who are doing SPM, if you're plotting a data for your experiment in your practical exam, you are not supposed to draw hanging graphs. You have to make sure that your graph either starts from the origin or is touching the x-axis or is touching the y-axis. So no hanging graphs like this. But in the exam questions, they can give you the hanging graph because they want you to show that you know how to complete the graph. In this case, we're going to extrapolate the data. For example, you could get a question like this. What is the velocity when t is 0? Now, obviously, we can't get the value directly because the graph does not start from 0. So how do we get it? You need to extrapolate the data. The extrapolation here just means that we need to complete the line. That means using your ruler, continue the line until it touches the velocity axis or the y-axis in this case. Now we can determine the value of the velocity when t is 0. So by looking this up, you can see the number here is about 1.4 meters per second. So you must show the line that you have extrapolated here in order to get the number to answer this question. Value here is 1.4 meters per second. So that's it in general about analyzing graphs. I hope you found this video to be helpful and educational. Do subscribe for more free physics lessons. If you'd like to help me keep making free educational video lessons and lab practicals just like this, donations are welcomed at my Ko-fi page. That's ko-fi.com/physicsrocks. If you'd like to get access to notes, quizzes, and syllabus updates, they are works in progress, but they will continuously be updated and added at my website at physicsrocks.com. Happy studying!